Imagine a material strong enough for the tallest buildings or longest bridges, yet versatile enough to take on any shape or form. It would never rust or rot, never need painting, and would resist fire. It's concrete, the most widely used building material on Earth, one with the natural properties of the stone from which it originates, plus its own unique qualities. The secret to this remarkable material is one essential ingredient: the glue that binds stone and sand together into concrete, the fine gray powder called Portland cement. Portland cement is a man-made substance born of some of the Earth's most abundant elements: limestone, clay, and sand. Their transformation into a new material was invented by Joseph Aspdin, an English stonemason, in 1824. He called his cement Portland because concrete made from it resembled a prized natural building stone found on the Isle of Portland, off the British coast. So Portland cement is not a brand, but the generic term for the type of cement used in virtually all construction. When Aspdin mixed his new cement with sand, water, and crushed stone, a remarkable change took place. Water and cement blend into a paste that coats the surfaces of the stones and sand. Through a chemical reaction called hydration, cement gel and crystals form to fill the spaces occupied by the water, binding together the sand and stones. And here lies the key to concrete's dexterity. It's pliable when freshly mixed, strong and durable when hardened. Properties that make concrete unnatural for architects and engineers.
It's a fun material to use for an architect because it makes one more of a sculptor than an engineer in a certain way. Because it has, some of the most unique structures that have been designed in concrete. It's fabulous as a sculptural, expressionistic material, more than other materials because of its fluidity.
The basic versatility of concrete is the ability to be molded to any shape and size that you want. That gives you an artistic license to deal with it as a design material and gives you a great deal of freedom.
Concrete begins with cement, and cement begins at the quarry, where explosives break rock from the face.
Fire in the hole!
These slabs of rock are crushed to the size of baseballs, then further reduced to gravel. While the plant's quarry yields the principal ingredient, limestone, other raw materials are often brought in from outside sources. All materials are carefully analyzed to determine the exact proportions of chemical compounds needed for the cement. After the materials are automatically proportioned, they are ground to a fine powder in massive rotating mills, then blended, homogenized, and tested again. In an alternate method, known as the wet process, water is added during grinding to produce a creamy mixture called slurry that is blended and stored in tanks. Whether as slurry or dry powder, the ground raw materials, called raw meal, are ready for the kiln, a huge rotating cylindrical furnace. At the heart of cement manufacturing, the kiln is the world's largest moving piece of industrial equipment, and one of the hottest. Here's how the process works. Some cement plants save energy by preheating the materials just before they enter the kiln. The raw meal swirls down a series of cyclone chambers, where it is heated by hot exit gases from the kiln. From the preheater, the raw meal enters the kiln at the upper end. As the slightly inclined kiln turns, the materials move through progressively hotter zones. At the lower end, a burner, fueled by powdered coal, coke, or natural gas, feeds a flame that reaches 3,400 degrees Fahrenheit. Some producers supplement fossil fuels with high-energy wastes, such as scrap tires, motor oil, solvents, or paints. This practice not only saves energy, but safely disposes of these wastes. Chemically, these wastes are similar to the fossil fuels they replace, but often burn cleaner than coal. As the raw materials slide and tumble down the rotating kiln, they're gradually heated to 2,700 degrees Fahrenheit, becoming partially molten. Under this intense heat, individual molecules break apart, then recombine to form a new compound called clinker. When the marble-sized white-hot clinker emerges from the kiln, it's cooled and hot air is returned to the kiln to save energy. Throughout the process, all materials are constantly sampled and tested for high and consistent quality. Cement must meet the stringent standards set by the American Society for Testing and Materials. Such vigilance extends to emission controls. All processes are carefully monitored and regulated from the central control room. Precise computerized controls enable cement plants to meet the highest air quality standards. Once the clinker is cooled, it's mixed with a small amount of gypsum, then ground into the superfine powder called Portland cement. Finished cement is pumped to giant silos for storage. From here, it can be bagged for customers who need only small quantities, but most Portland cement is sold in bulk shipments. From a central control room, operators ensure safe and efficient loading of cement into trucks or rail cars. From the plant, most cement goes to ready-mix concrete producers. Here, the cement is mixed with sand, gravel, and water to create concrete, which is delivered to construction sites in the familiar trucks with revolving drums. Cement is also used in concrete block, an array of precast concrete products, and to make mortar for brick and block. Ultimately, it forms our roadways, patios, buildings, skyscrapers, and more. And not only is it the most versatile of building materials, concrete is also among the most energy efficient. Its production requires only a fraction of the energy required to produce steel, brick, plastics, or aluminum.
We can look at various materials in terms of the total energy content of the material. From the time it is excavated from the ground, from the materials, basic materials, and from the time it's produced, all the labor it's taken to fabricate the material and put it up. What is the energy content of a material? One finds that since concrete uses natural materials from the ground, it has considerably less energy content compared to other materials.
Once in place, concrete's mass resists temperature swings, reducing the heating and cooling requirements for homes and buildings.
Concrete is a very environmentally believable material with respect to reduction of energy usage of fossil fuel and other energy sources because of its mass and its terrific resistance to thermal interchange because of its mass, because of its density. So that in that sense, environmentally, it's a very good material. It's a dissimulative material. You can play with it. It can become what you wish it to be. That's where it's interesting. I mean, it's interesting also environmentally because of the lack of fossil fuel and all of that. But I think at another level, it's a lot of fun.
From quarry to kiln to construction site, concrete is the cornerstone of all that we build. A manufactured stone rivaling its natural counterpart in strength and durability, yet far surpassing it in uses and versatility. Our modern high-tech Stone Age begins with a fine gray powder called Portland cement.